Welcome back to Stochastic Processes. This is lesson number 6, and it's the second lesson on random walks. In part 5, we built the unrestricted walk, found its mean and variance, and derived the binomial distribution for its position. We finished by computing the probability of being back at the start after 100 steps, which came to about 0.079, or about 8%. But I end it with a warning, and the warning is where this lesson begins. Being back at 0 at step 100 is not the same as returning to 0 for the first time. Separating those two ideas takes real work, and it leads us to one of the most elegant tools in this subject, the generating function. So let's talk about first returns, and we'll be doing that in this video. So we did this on the last slide, and I mentioned it again in the intro on the previous slide. We computed the probability of starting at state 0 and then after n steps being in state 0, and that came to around 8%. However, it is not the probability of first returning to 0 at 100 steps. The walk may have visited state 0, several times along the way, and this counts meaning this probability counts all of those paths. So you could have been back at 0 3 times, and this is just computing that at time n, at n steps, you're at 0. So the first return is a generally different and harder quantity. The first return probability is what decides whether a state is recurrent or transient, which is the whole subject of part 7, the next lesson after this. So we're going to need this result later on, as well as being interesting in its own right. First returns happen only at even steps. So why is that? Well, first of all, we assume we start at state 0, which happens to be an even state. Each step changes position by plus or minus 1. So plus 1, you go right, and minus 1, you go left. To be back at 0, the rights and left must balance exactly, and that requires an even number of steps. So we need only to consider steps 2, 4, 6, 8, and so on. And this comes from the parity argument that we discussed in a previous lesson. After an odd number of steps, the position is odd, and after an even number of steps, the position is even. And since 0 is even, we can't return back to 0 in an odd number of steps, which is why we only need to consider the even steps. So we want to relate our returns to a given state to first returns. And we're going to have an equation here, down here, which I'll get to in a second. So let A sub 2m be the event that the walk is at state 0 at step 2m. And the reason we have 2m here is because of what we just discussed, that we only need to consider even returns to state 0. Let B sub 2i be the event that the walk returns to 0 for the first time at step 2i. So again, these are two different events. We had been working with this in the previous video. Every visit to 0 at step 2m has a first return somewhere at or before it. So it could be that at 2m is the first time you return to 0, but it could be at some earlier even number. So we condition on when the first return happened, and we use the law of total probability. And the sum is over the various even numbers that are less than 2m. That's why we're going from I equals 1 to m. So you return, if I is 1, you return to state 0 in 2 steps. And given that you return to 0 in 2 steps, what's the probability that you're back at 0 at 2m steps? Then, or you could return to 0 in 4 steps, and then times the probability of returning to 0 in 4 steps, and then being back there again at 2m steps, and you add all those together, and that's that'll give you a sub 2m. Now the problem is we're looking for the probability of these b sub 2i's in there, and it's embedded into this equation here. So that's the hard part. So let's continue, and we'll solve this by doing something known as a generating function. So I brought our equation over from the previous slide. We know what this is, the probability of being in state 0 after 2m steps. That was the binomial formula we computed in lesson 5, the previous lesson. So that's p sub 2m. And then this conditional probability we know also. This is just saying that the first return to 0 was at step 2i, and what's the probability that you're going to be back in state 0 after 2m steps total, but you already know that you've taken 2 sub I steps, so this probability is p sub 2m minus 2i. So this is replaced by this here, and we write this probability p of probability of the first return being at step 2i, we write that as f sub 2i. That's just the notational thing. So what we want to do is isolate this f sub 2i, because we know this term and we know this term. And the way we do it is using a generating function, which is rather difficult to derive. And I'll give you a reference to the derivation, but I'll give you the answer, and then we'll work through how to use the generating function in order to find these f sub 2i's. So a generating function is a series, summation, where the coefficients give you the probability that you're looking for. So I'm just giving you a general definition here. The probability that x equals 1 would be the second term, probably x equals 0 would be the first term in a particular series. So this is just a general definition of a generating function. Now for our particular problem, the derivation is rather involved, and I'll give you the reference here. It's section 3.4 of a book by Jones and Smith, Stochastic Processes and Introduction. I'll give you the details of that in the information to this video, but the answer is, and it's in the case where p equals q equals 1/2, this is our generating function. And so what we need to do is expand this as a Taylor series, and then we'll be able to read off the probabilities, these f sub 2i's that we're looking for in our problem, the first return probabilities. So I'll show you that on the next slide. If we expand our generating function from the previous slide, this thing here is a Taylor series, we get this series here, and then the coefficients can be read off as the first return probabilities. So f2n equals cn minus 1. That's the, I'll get to that in a second. These are the Catalan numbers. And then 2 to the 2n minus 1. So for example, if we wanted the first return to be at step 12, that would be this one here. And so it would be 42 over 2 to the 11th power. We just read off the coefficient. The hard part is finding this here. And as I said, I'll give you a reference to how this is derived. It's not all that easy and not suitable for a video to go through the details. But unless it's like the whole video, but I didn't want to do that. So it's 0.0205 approximately. And of course, these numbers, as you might expect, are getting smaller and smaller. And it turns out the numerators, 1, 1, 2, 5, 14, and so on. These are what are called the Catalan numbers. And they have a lot of applications in number theory. And they're defined by this expression here. It's from something called or you can find more information on this, I should say, from something called the OEIS. It's basically a dictionary of many, many hundreds and hundreds of sequences, maybe even thousands. And the next slide, I'll actually give you a little bit of background on this dictionary of sequences. But in terms of the Catalan numbers, they're one of the most frequently occurring sequences in combinatorics. They count the number of ways to arrange balanced parentheses. They count the number of binary trees with a given number of nodes, and the number of ways to cut a polynomial into triangles. Just some examples. And here's yet another, I guess, application of the Catalan numbers. It's actually part of the coefficients for this first return probability. I wanted to take a slight diversion here and talk about the online encyclopedia of integer sequences, which I mentioned on the previous slide. It's called the OEIS. Here's the website, oeis.org. And it's a very good resource with a huge amount of information. You can put in a sequence and it'll look it up. So I have already put in the Catalan numbers and it found that, but we can do another sequence. Let's do the Fibonacci numbers. Yeah, and you see it found almost just a few things. Now, if you know the name of the sequence, you could put that in there and it'll come up also. We go back to the Catalan numbers that these here. You do a search and you see it found them. There's a huge amount of information on most of these. It's just the comments, then references, then it goes on for pages with links. You could spend weeks going through all this information. So there it is. It's a useful resource if you have a sequence and you don't know what it is, but you think it might be something somebody already knows. You can just put in a certain number of them and a good chance is you'll find it. And if you know the name of the sequence, but you just want to get more information, you can do that also with this. And if you discover something that hasn't been found yet, you can actually send a report to the manager of this website, and they'll possibly create a new number. These are the numbering systems shown here. They may create a new number if you've discovered something new. Everything so far has been one-dimensional, a walk along a line. You can go either left or right. But nothing stops us from moving to higher dimensions, and the results there are generally surprising. In 2 dimensions, we have this figure, or possible figure. There could be other 2-dimensional walks, and you start at state 0, 0, and you can go left, or you can go right, or you can go down, or you can go up, and all the probabilities of leaving this state would add up to 1. So this U and this L and this D and this R would add to 1. And then if all the probabilities are 1/4, then we call that symmetric. Okay, so that's 2-dimensional. We can go into higher dimensions. I have a little bit of information on that on the next slide. So in 1 and 2 dimensions, for the symmetric walk, as we described, returning to the starting point, the probability is exactly 1. However, in 3 dimensions and above, the probability of returning to the starting point, again, where you have a symmetric walk, is no longer 1. So in 3 dimensions, you're already down to 0.34, 34%. And you notice the probabilities of returning as you go into higher and higher dimensions get smaller and smaller. I'm not sure who this quote came from, but it's related to this here. A drunk man will find his way home. In other words, a person who's inebriated can go either left, right, or forward and backwards, and he or she would return back to the starting point was probability 1. But a drunk bird may get lost forever. The idea is the bird is in 3 dimensions. It could also go up and down, and so the probability the bird comes back to its starting point is less. So that's the idea of this quote here. Before we close, it is worth saying how far this idea reaches, because a walk on a line can look like a toy, but there's actually a lot of applications. The term random walk was coined by Carl Pearson, the mathematician and biostatistician, in 1905 in a letter to the journal Nature. He was modeling how mosquito infestation spread through a forest, and he wrote in asking whether anyone knew how to handle the problem. Since then, the application has multiplied. There is a bibliography devoted purely to applications in theoretical chemistry and physics that runs to 20 pages. This here, I'll give you a link to this. Random walks are used to model polymer configurations problems in solid state physics, diffusion through inhomogeneous media, and a great deal of biology. One of my favorites is the connection to electric networks, where questions about random walks translate into questions about resistance in the circuit, and each subject illuminates the other. All of these references are given in my book, and I think I gave you a reference to my book earlier in another lesson, but I'll provide it again in the information here, and then you'll find the references to this towards the end of this section on random walks. Some takeaways: being in state 0 after n steps is a different computation from the first returning to state 0, given that you started at state 0. So we did that. We did the second probability computation in this lesson, and we did the first one in a previous lesson. First returns occur only at even steps. That's related to this parity principle. Conditioning on the first return gives us a convolution. Generating functions unravel this, and they give us a way of finding these first return probabilities. Oh, and by the way, earlier in this lesson, I mentioned that I wasn't going to derive the generating function, and I just gave you the result, and then I expanded it as a Taylor series. So I changed my mind. I have a whole lesson after this, lesson 6a, that it's actually quite long. It's 14 slides long, that shows how to get the generating function. As I said, it wasn't easy, but if you're interested, it's kind of optional. It's not actually in the flow of things, but if you're interested, the next lesson will be on that. And then the lesson after that will be 7. So let's see. And then there's one last point here. Return is certain in 1 and 2 dimensions and not in 3 dimensions. We just saw that in the previous slide. So in higher dimensional symmetric random walks, the probability of returning to your starting state is much less than 1, but it's probability 1 in 1 and 2 dimensions. Then coming up on part 7, as I say, there's going to be a part 6a on generating functions, and then 7 after that. We'll talk about communicating classes. And I mentioned this much earlier in, I think, one of the first or second lessons, where you're talking about what states you can get from to each other. So they're in the same communication class. Then irreducibility and why it matters. recurrence and transient. That has to do with coming back to the state and an infinite number of times, and transient is you sort of hit the state a few times, and then the probability is you're going to go off somewhere else and not return. So we'll make that more precise. And then the criteria that decides which one a state is in. So we'll look at that after the generating function lecture. We'll come to this. So if you like this video, please give it a thumbs up and stay tuned. So we're only less than halfway through the series.